Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I am very happy to have Gordon Yip with us today. Hey, Gordon.
Hey, how are you, Frank? And
I'm doing very well on this December 3rd, 2021, as we round out 2021. What a year it has been, for sure.
okay.
And the year is still with us, so we got a little ways to go. Gordon, where are you located at?
So I'm actually in the UK right now. More specifically, I'm in UCL right now.
Ah, London. Okay.
Yeah, London, basically.
So I imagine winter is definitely in London. Does it snow in London? Do you get snow there?
Not really, no. But last year, quite fortunately, we got some snows in London. Yeah. But this year, I don't know. But it's quite cold right now. So it's hovering around 0 to 5 degrees right now outside.
Okay.
Pretty cold.
Yeah, we're getting our typical winter weather in Phoenix. So we'll start off somewhere, 45, 50 Fahrenheit. And then we'll warm up to about lower 80s during the daytime. So this is when we get all the Canadian snowbirds coming down. So we get a lot of Canadians coming out for the warmth of the Phoenix Valley as we go through.
All right.
What's your current position there at UCL, Gordon?
So I recently graduated from my PhD just a month ago, actually. And then right now I'm starting a postdoc with a position at UCL.
Very good.
In the same place, within the same group. So doing pretty much the same thing. Cool. Just basically continuing my PhD research.
Okay. Well, except now we get to call you Dr. Yip. So that's pretty cool.
Thank you very much.
You are welcome. And Dr. Yip, what do you like to do research in?
So my primary interest is basically at the intersection between machine learning and exoplanetary science.
Cool.
So basically, my everyday research question is, can I apply machine learning techniques on this problem, that problem? So basically, spotting problems within exoplanetary science, such as, okay, with the chemical model, can we speed out with machine learning techniques?
Right.
Yeah.
Very cool.
So that's it.
And that is going to take us to this very lovely AJ article on peeking inside the black box, interpreting deep learning models for exoplanet atmospheric retrievals. And Gordon, take us away.
Thank you very much. So this work is basically done by me and my other colleagues at UCL. You can see Quentin, Nicholas, Mario, Billy, Ingo, and Giovanna. So basically in this paper, I will give a summary of what is going on, or some kind of background before we go on, is that in recent years, we're seeing that machine learning techniques or deep learning models that are being applied in exoplanetary science. And in many cases, sometimes in conferences actually, people present to it, and then sometimes people ask but they're black boxes. You actually don't know what is going on.
Right.
And, I'm with them actually, because we don't know, because with this kind of learning algorithm, they are really powerful because they've got tens of thousands or millions of neurons inside. That's why they are very powerful. But at the same time, because of their sort of characteristic, it is really difficult for them to explain their decision. Most of the time, what happens is you put something in and then it spills out a number, but you don't know why. Right. So that's the background. And what we're trying to do here is that we are saying that, okay, there are a few researchers who have been including us, applying machine learning models on exoplanet atmospheric retrieval. And then what we're trying to do here is, okay, can we develop some tools that can basically peek inside the black boxes of these deep learning models? Nice. When are they wrong? What is their prediction based on? And when they're wrong, how wrong they can be, how competent they can be. So that's basically a general picture of what we're trying to answer in this paper.
Very cool. Yep.
Yeah.
It's peeking inside the black box.
Yeah, exactly. So to give just a little bit of context into what kind of problem that we're trying to solve, like the nitty-gritty, is that so in recent years, with the imminent launch of JWST, which is really exciting, that we are trying to look at the atmospheres of remote exoplanets. So what we're trying to do there is, if we observe these remote exoplanets, we want to know what kind of molecules is inside those atmospheres. So do they have water? Do they have methane? Do they have carbon dioxide? Because that would basically tell us a lot about the planet itself. And in a bigger picture, what kind of molecules is important, what kind of like carbon to oxygen ratio. We are saying that is actually very important for planetary formations and how the planetary dynamics will play it out. So these kind of things are all very important question. And what people used to do, they used to rely on this technique called, there still is basic atmospheric retrieval. Okay, so suppose you have an observed spectrum coming out from WC3, so Hubble Space Telescope, or in the future, it's going to be JWST or Ariel or Twinkle, which is quite exciting. So, and then what happens is you build a physical model, and then what the physical model do is that you will take in physical parameters such as temperature, abundance of the molecules, radius of the planet, put it in, okay, and then the forward model, which is called the physical model, will give out a theoretical spectrum. And then you compare that with your observation. So you do that multiple times for 1,000 times using MCMCs, and then in the end, you get your answer. Now, we call this process retrieval because you're retrieving those parameters. But the problem is they are quite slow.
And that forward model can be really complicated, right?
Yeah, it can be quite complicated. And so people have been doing, what people have been doing is, oh, can we actually use machine learning to bypass the entire process? So basically, if you train a machine learning in pretty much the same way, where you put in a spectrum as input to the machine learning model, and then you ask it to basically predict all these temperature, radius, abundances of the molecules, all the parameters that we actually care about. And then after you train it, then voila, you'll be able to have a machine learning model that can tell you, if you give it a spectrum, you tell you about what kind of temperature it is, that what kind of radius it is. So that's basically the background of all this. But what we're trying to say here in this introduction is that while it is all very good, but we shouldn't basically just trust a single value coming out from the neural network. And what we should do is we should question about their prediction, and we should try to break down their prediction and see if we can actually break them down into, like, say, bias and variance quantities. And try to use some kind of technique to see whether it's actually learned some of the stuff inside the data set, or whether they're actually biased or not.
Very good.
So, okay, that takes us to the second part, which is the problems and what we're trying to do. So there are three objectives that we're trying to do. Quite a lot of stuff happening there. So the first objective is that we're seeing that so we, in terms of machine learning, we keep talking about machine learning, that, but what exactly of model we're trying to use? And there are actually quite a few different models, say random forest, MLP, CNN, STM, and then combination of them. So our first objective actually is, okay, we don't care. I just train 3 different types of model.
There you go.
Do they all work? And then what we're saying is they all work similarly, very similar. So basically, you can use MLP, CNN, and LSTM. These are the 3 mainstream models that about all the machine learning tasks, and they work on this kind of data set. So no matter which one you use, they work. And so that brings us to the second part. So for the second part, well, maybe I could probably say more detail about what kind of task we're trying to solve. So we're training a model to infer atmospheric parameters from an input spectrum.
Yes.
That's the task we're trying to do. We put in a spectrum into a neural network, and then we're saying that we have temperature. It will give us the temperature, radius, abundances of H2O, CH4, gases, abundances from them. So the second part is, okay, we provide a very detailed evaluation about, okay, if a model gives us these kind of predictions, what can we do about this prediction? Can we sort of analyze them, bring them down, and then access the credibility of this prediction? Okay. So that's it. And then the final part is basically, can we use, we try to use a perturbation-based sensitivity analysis.
Okay.
Yeah. So, and then we try to question it. Basically, you can think of it as interrogating the black box, and think about, okay, what kind of region did you actually learn anything, or did you actually just memorize something?
Very good. Yep. Yeah, it is called learning, not memorizing.
Yeah, better not be memorizing. Yeah. Okay, so that brings us to the data generation part. So I'll be very quick on the data generation part, because right now we don't have many spectra around us. We have about a handful of them in WCP resolution. Okay. So what we did, is, if you want to train a machine learning model, you need about 10,000 or more spectra in order to do that. So what we do, we go for our simulated model, then we generate basically 10,000, around 10,000 spectra in sort of aerial resolution. And then on top of that, we also couple it with aerial red. So basically aerial radiometric model, which in simplified terms is that it gives realistic instrument noise based on the planet properties. Okay, so that's that. And then if you go to table 1, that's basically the parameter state that we use to generate. So basically we have 1,000 different planets. And then for each planet, we generate several instances of their atmosphere. And then for each atmosphere, they will have random numbers of H2O, CH4, CO, CO2, etc., to give us basically, because we don't have any prior knowledge on what kind of atmosphere that they will have. So we just randomize it. Okay, so the second part is 2.3 is basically, okay, now we have all this data, we have to do some pre-processing. So the pre-processing is basically quite standard. It's generic across all machine learning models. Yeah. Where you have to put it into certain formats so that the machine learning models will work. And then we train our models. You can see that I skipped the details about, okay, how to implement them, what kind of learning range, what kind of layers, but then they're all in the appendix. Yep. Yeah, because not the main point of this paper, but then I also want to show it, but it's in the appendix part. Okay, cool. So suppose that, we did everything on top, generate our data, pre-process our data, train the model. Now that brings us to the next part, which is basically quite important part in a cycle, is basically how's the performance of my model. So that brings us to section 3 in figure 2. So figure 2 is, if you look at nowadays machine learning papers in astronomy or exoplanet science, you will see this kind of plot, and we call it truth versus prediction plot.
Yes.
Okay. So the diagonal line shows you that if you have a perfect model that can get the right answer for every test cases, every predictions of every blue dots should be on the dark diagonal line. But in my case, if you're not having a perfect model, then you see some scatter around it. So each blue dot is basically a spectrum in a test case, in test set.
Yes.
Okay.
Yes.
Yeah. Now, what I'm showing in this figure is that gives you an overview about, okay, what kind of rough performance of the model. Is it working? Is it giving you sensible results? But what we are arguing here is that, well, while it gives you a general overview about the model, it can't give you, say, quantitatively what is happening, because each test case represent a very specific configuration of the atmosphere.
Yes.
So that atmosphere may have a lot of water, and then in other cases, that atmosphere may have a little bit of water. So that may influence the performance of the model. As you can see, that they are quite scattered around, quite a lot of deviation around the diagonal line. So what we are thinking is, okay, now that we have this prediction, can we actually break it down into bias and variance term? So that's basically what we did. And then if we go to figure 3.
Okay. One comment here. What's CO?
Oh, yeah.
CO is kind of an outlier there, right? I mean, all the dots are here, and that's not very truthful.
Yes. Okay. Actually, I should talk about it. So, what we can see, first of all, you can CO is almost impossible to retrieve.
Extract out. Yes.
To extract out. And that's actually based because of the instrument wavelength and the waveband of CO, the molecular signature of CO. So it's quite hard, if not impossible, to get CO. But also you can see that for H2O, for other molecules, you can actually retrieve them quite well in a machine learning model. Yeah, for contemporary retrieval, you can do it much better. But for machine learning model, it's quite well. And then surprisingly, you can also sort of constrain the mass of the planet. Usually the mass of the planet is provided from other sources as well. You can sort of constrain that. For the radius of the planet, it's not really well. It's not really that well constrained. But then we sort of know the answer because I didn't put in the radius of the star inside, which basically gives out some kind of degeneracy there. And then the MP, RP, and TP, they're sort of degenerated. For the cloud top pressure, basically, is a simple cloud model where you can think of it as you have a spectrum and then you have a cutoff line somewhere. That will basically that is opaque, and it will cover any molecular features that is basically under that pressure. And you can see that the model can sort of differentiate, or like, okay, it has cloud, it doesn't have clouds in some cases, but not in all cases.
Yeah. It's a little hard. Okay,
cool. It's quite hard. Yeah.
And so you want to go figure 4, was it?
Figure 3, I think. Yeah.
Figure 3. Okay. All good.
Thank you.
Very good. These are the bias and variance. Okay.
Okay. I think that there's some latency there. Okay, I can see the bias and variance now. No worries. Yeah. Okay. So what we did here is we did what we call a eco-frequency sampling. So let's say if we just look at H2O, each point here represents 100 test cases.
Okay.
When the true log is around -3. Now, if we go from the right to left, you can see that the abundance of H2O, the log abundance of H2O is decreasing, meaning that you have less water in the atmosphere. Now you can see that as you have less water in let's say to the right-hand side first, that you have a lot of water in the atmosphere. And that means that the molecular signature in the spectrum is quite good. It's quite evident, it's quite significant. And so the machine learning model is able to predict it quite well. You can see that it has a very low bias, and the variance is quite small as well. But then as you have fewer and fewer H2O in the atmosphere, so does the molecular signature is weaker right now. Now you will actually get covered by other molecular other molecules such as NH3.
Okay.
Then the model becomes more indecisive about its prediction. You can see that it has a high variance and a high bias as well.
Yeah.
But all of a sudden you think that, well, then in that case, the average deviation should increase instead of decrease when you have fewer and fewer H2O. But if you look at the plot of H2O, you can see that actually the average deviation is going down at -7. Yeah. And so that actually hints to you what happened. What happening is that the neural network realized that after certain log abundances, you can't actually predict anything. You can predict -8, -7. You won't make a difference. But the thing is, you get penalized. It can't differentiate those cases anymore. So, but then the neural network is trained to optimize sort of the loss function. What the loss function is that it will minimize the difference between the truth and its prediction. So what it does is that, okay, you will predict the mean around -7. So when you realize that that spectrum has no sort of water feature, then you will say, you always say, instead of saying that you will be -6, -7, or -8, you will say -7 is always -7, so that you will get the minimum loss value.
Okay. Okay.
Yeah.
I'm with you. I'm with you.
And then that's the same thing happening for other gases as well. But then you can see that for different gases, because of their molecular signatures, you can see that they have different Chove values. So let's say for NH3, it happens later on, but then for H2, it's a little bit earlier. For CO, is basically has no idea what is happening. So it's always predicting -6.
Yeah.
But then if you are quite innocent, you think that, if you're not looking at it carefully, you think that, wow, that means that at -7, the neural network is doing really well. And then when it's predicting -7, you should always trust it. It's not the case. Yeah, as we will see later on, that is actually not the case. Yeah. So this couple is very good at basically dissecting about what the neural network's prediction is at different level using our own domain knowledge, because we know that if we decrease the amount of water, the neural network should struggle. If it doesn't struggle, that's a warning sign.
Okay. Good.
Yeah.
Good. I'm with you.
Yeah. And then we also have mass, MP, RP, and TP. Yep. So for the mask, it's doing generally quite well, but then we don't expect it to do really well because at the same time, it can't really constrain the information. The information given by the spectrum is not much. For the radius of planet, same thing. We didn't give it the radius of the star, so there's quite a lot of generosity there. But at the same time, we also know that for MP, RP, TP, and the pressure, the cloud pressure. They're quite degenerate. It has been discussed in literature quite a few times, and that's why we also expect that the network will struggle. Yeah, and then afterwards, the next thing we want to look at is what's the interaction between the NP, because the aim here is to test whether neural network actually understand the concept of having a spectrum. Does it actually memorize the whole thing? So the next steps that we give to a neural network is, okay, let's suppose that I give you two different spectrum. Okay, one spectrum with a lot of water, one spectrum with small amount of water. How would that affect your prediction on other molecules?
Yes.
Okay. Okay, so that will, I think, bring us to figure 4 in the paper.
And figure 4, pull that up a little bit, and we'll wait for the bandwidth.
Yeah, okay, cool. So what we're looking at here is we're looking at exactly the same setup as before. We have the true log abundances on the X, Y, average division on the Y-axis. And then we are looking at the model's prediction for water, CH4, and CO. But then right now, a little bit different is we're looking at the case of when we have a high amount of NH3 ammonia and a very low amount of NH3. So let's look at the upper left corner. So we're H2O.
Okay.
So you can see that when you have a lot of ammonia, then the prediction of the neural network on H2O in some of the abundances actually suffered.
Yes.
You can see that the average rate actually gone up quite significantly.
Right.
Yeah, but then if you have just a little bit amount of ammonia in the atmosphere, all of a sudden that you can see the average deviation of the neural network actually improved. It's actually gone smaller.
Right. Right.
And that is actually because the molecular signature of H2 and NH3, they're actually quite overlapped to each other.
Yes.
Yeah. So that if you have high amount of one another, that basically masks the whole thing or partially masks the other. And that's one test that we want to use because our physical intuition will say that if you have a lot of ammonia, you shouldn't be able to retrieve the H2 quite well. But on and vice versa in the other case as well. So that test is basically quite reassuring and say, okay, that actually now you may naturally ask, okay, what happened to the other case? Then we can see that there's no sort of differences in the latter case where you have high amount of CO2 and low amount of CO2.
Yeah.
So that's the other test that we want to have. So CO2, we know that its waveform has nothing to do with H2O or CH4.
Yes.
Okay, so no matter how high the amount, how low the amount of CO2, it shouldn't matter. That's what we expected. And what we're seeing here is that in the high cases or low amount of CO2, doesn't make a difference.
Yes.
Yes. So you can see that the points are quite aligned with each other, which is reassuring.
Yeah. Gives confidence. Yes.
Okay. And CO is just there to show that no matter what, you wouldn't change.
Right.
Which is also reassuring, which shows that the information content is not affected by, either you have high amount of something or low amount of something. Right. If you don't have much information about a molecule, it wouldn't work. No, all that is really well. But then I want to bring to there's another way to see the covariance between different atmospheric model parameters, which is bring us to figure 5. So figure 5 is a figure that we are quite familiar with in terms of exoplanet atmospheric retrieval. Is that we call this posterior distribution.
Corner plots.
Yes, corner plots. Yeah, I could. So what we're trying to see here is, so let me explain how I generate it. Let's say we train the model. Okay, so we have a model here. We have a spectrum, we put it in. But instead of putting in just one spectrum, because the spectrum they also have instrument noise attached to them. Right. So I generate hundreds or thousands of different spectra, put it into the black box, to the neural network. And then what I want to get out is basically corresponding parameters.
Yes.
Yeah. And then I collect all of these parameters, and then I I use a corner plot to basically plot out these kind of surrogate posterior distribution. It's not straight posterior distribution, it's a surrogate one produced by varying the observed spectrum. Yes. So yeah. Okay. Now, what we can see is that if you have a high amount of molecules, such as if you have high amount of ammonia, you will be able to constrain it, you'll be able to predict it within 2 sigma. But then in the case of CO, we can see that you can't constrain it at all. Like it doesn't have any clue about what is going on. And also for methane, well, methane is quite well actually. Yeah, but the main point here is that you can see some of the, there are covariance between some of the parameters such as MP and RP or RP or TP. So they have some sort of physical correlation between them. Yeah, but then what we are also missing is that there are some of the well-known correlations, such as between H2O and cloud. There should be some kind of correlation, but then we are missing them. So basically, bottom left of the posterior plot. Okay. Yeah.
Yeah.
So
missed it.
Yeah, and then also you won't see a perfect Gaussian everywhere in a corner plot, at least in our field. So that also highlights that, okay, while you can produce this kind of plot, you can capture some of the physical correlation between parameters. It's not perfect yet. Yeah, you can't simply basically just use this model and use it as, let's say, a prior to your retrieval code.
Yeah. Right.
So you can't use it. Yeah. So that brings us to the next part.
Okay.
So scroll down. I think we can go to figure 6. Yeah, figure 6 is basically where we sort of flip the table a little bit. Instead of talking about the ground truth all the time, which is basically what we did in figure 3, figure 4. When's the last time you have a ground truth about something? Actually, we don't. I don't know. Like, if you're observing something, let's say if you're observing a planet, you won't be able to say, okay, I know the ground truth. Now the prediction is like that. Instead, all we have is the prediction.
Right.
And then what we're asking is, okay, if I predict something to be, let's say, if I predict this planet to have log abundance of -4 for water, okay? How far am I from the ground truth? Because that's basically what we care about, is the average event from the ground truth. If I predict something like that, how far away am I from the ground truth? And basically, this is what this plot is talking about.
Okay.
And that's why the x-axis is now the predicted abundance level.
Right.
And the y-axis is the same as before, the average deviation, but the average deviation from the ground truth.
Yes.
Okay. Now, if we say go to H2O, so I won't describe the black curve yet, but I'll do it later. Okay. So for the H2O case, that is going according to our intuition, where when you have a lot of H2O, basically on the right hand side, you have a small deviation from the ground truth, which is what we expected. But then as you go to fewer, as you have fewer and fewer water in the atmosphere, let's say log abundance of -7. Previously, we are saying that there is a very low average deviation from the ground truth. But then right now, we can see that actually this is not the case anymore. The average deviation from the ground truth is quite high when the neural network is predicting -7.
Yes.
Meaning that if the neural network is telling you that that planet may have a log abundance of -7, you probably shouldn't trust it. Yeah. But if the neural network is telling you that, well, that planet has log abundance of -3, chances are quite certain about this. It's quite evident.
Right. Right.
Now, then I will proceed and talk about what the black curve actually is. So the black curve is actually the frequencies of prediction in each bin.
So the right axis. Okay.
Yeah. So how frequent does the model predict this value? So because when we generate this structure, we know exactly we are doing this sort of uniform sampling. So we know that at each bin they should have equal number of spectra. So basically each bin should have equal number of examples. So if you have 200 examples in -3, you should have 200 examples in abundance equals to -4.
Yeah, okay, for uniform. Yes.
Yeah, uniform sampling. But you can see that the neural network is not following this pattern. The most evident one is CO. You can see that the neural network's prediction is concentrated around -6. So basically what it means that if you fit any spectrum means that you say -6 abundance of CO.
Yep.
Yeah. And that's basically a signal telling you that, well, the neural network doesn't have any clue about what is going on, but it will give you one number.
Yeah. Right.
Okay.
I'm with you.
Yep. So that naturally led us to one question is, when should we trust the neural network? And that is the title of the credibility of prediction. But credibility is quite a subjective thing. If I say something is credible to me, it may not be credible to you. So, but then we sort of try to follow some kind of guideline and say, okay, that's how we define credibility. Okay. So when we try to we try to define our credibility in terms of probability. Okay. So what we're trying to say is that, so if you go to figure 7 now, that basically gives us the, yeah. Okay, so for in figure 7, you can see the y-axis is now the probability, and the x-axis is same as before, predicted abundance level. So in the y-axis, what the probability refers to is the probability that we are seeing prediction that is within certain range to the ground truth. So let's suppose that the ground truth value is 10 to the power minus 3.2. Okay. And then the new network is saying that, well, I predict that the water abundance is 10 to the power minus 3.5. So there is a log abundance difference of, say, 0.3.
Okay.
And if you say that your tolerance level is about 0.5, which means that then that's falls into the category, then we say, okay, that's a good one. And then we say, when we calculate probability, we're saying that out of all the examples about predicted by the network, our example actually fit our criteria.
Okay.
Yeah, so we have some criteria and we calculate the probability. And then we also define a cutoff line, which is basically if we're seeing that 70% of time the new network actually fit our own criteria, we say that it is credible.
Okay.
Yeah. So that basically we can say that that criteria and the cutoff line is basically defined by the user.
Sure. Yeah. Okay. And so in this, anything above
so anything above that, any abundance above that,
is
0.7 is credible.
Right.
Yeah, it's something that we say is credible to us. But of course, depending on your application, depending on, let's say, your domain knowledge, you may say, or tolerance level, you may say that, well, actually, I want it to be a bit lower. That's also fine with you as well. All we're here saying is that we want to provide this kind of methodology for you to use. Now, we have also compared this kind of credibility limits, basically the lowest abundance level you should rely on, you can sort of rely on. And then we compare that with a result from the retrieval, which is, I think, the table 2 is showing us. So if you go down, yeah.
Okay, yeah, very good.
Yeah, so we compare our credibility limit, basically we derive from a neural network, and we also have a detection limit, which I extract from my colleague's paper, Shan et al. 2020, where he actually uses retrieval techniques on a population of planets. The good thing about these two studies is that we use the same pool of planets, and then we have the same data generation process.
Good. Okay.
Yeah.
Good.
So basically, you can sort of compare them, but not exactly apple to apple, though, because what we are saying here is credibility limit. What they are saying is detection limit. So we have different definitions.
Yes.
But what we can conclude is that in terms of this kind of aerial resolution spectrum, we can detect, let's say, as low as minus 5.8 log abundance level. Okay. In terms of predicting molecules. Yeah. You can also see that I have missed out mass of planet, radius, and temperature because they are harder to explain using this kind of methodology. Okay. Yeah. So that's why I've left them out. So now that takes us to the final part of the paper, which is basically, okay, how do you know that, let's say we train this model, we sort of inspect the interactions, how are we going to say that to justify that it actually learns the molecular signature? How do you know that it actually relies on them? Okay. So we did what we call a perturbation test. So to explain this methodology is you have your trained model, again, sitting in the middle, you have your input spectrum, you put that in, but instead of putting in your input spectrum, you sort of perturb parts of the spectral range a little bit. Okay. So it's basically you shake them around.
It's like a little pong.
Yeah. So basically you give a little shake, but not to all of them, just to certain region.
Yes.
Okay.
Yeah.
So you put it in, and then you ask the trained model, okay, what's your prediction for, let's say, for water, okay, and then you ask it once, and then you perturb it again. You ask it again, okay, what's your prediction for water now? You do it multiple times, but then each time you perturb different region and at different scale.
Yes. Okay.
Sometimes you may shake it a lot. Sometimes you may shake it a little bit, and then sometimes you do it at, say, one region on the left and then one region on the right. Other times you do it at other region. You do it for so many times. In the end, what you're recording is that how the neural network actually respond when you shake different regions. And that's basically the basis of our sensitivity test. And then what you're seeing in figure 8 here is the sensitivity map of different molecules. So that's basically what the network thinks that those regions. So the highlighted region, the yellow region, is what the neural network say they are false sensitive to changes in this area. So if you change in this area, even so slightly, you will affect the prediction of ammonia or CO2, CO. So we are actually, so when we're looking at this map, we're actually for H2O, so for water, methane, and ammonia, and carbon dioxide, we say that, well, it's actually quite makes sense because we expect it to be able to capture this information. But we thought that you won't be able to capture CO, carbon monoxide, because judging from this poor behavior, poor performance, we thought that, okay, it won't be. But to our surprise, it actually is quite able to capture it. You can see that it's highlighting the peak of CO. You see it's yellow up, and then you can also see, but then for methane, it's also quite interesting that it's actually highlighting the highest peak of methane between 3 to 4 micron.
Right.
But for 2 to 3 micron, it doesn't seem to care.
Yeah,
so, which means that the neural network actually is figuring out a way to say, because the task is it has to in one go predict the molecular abundance of all these gases plus the mass of the planet, radius, and temperature of the planet. So quite a big task to ask. And what the neural network is trying to do is, okay, now that I'm assigned different region, maybe it's finding different regions of the spectrum for predicting certain quantities. And so you say that 3 to 4, between 3 to 4 is quite reliable. I can extract information about CH4 that way. And for 2 to 3, I don't need to care about that. Instead, I'll use this region probably maybe for H2O or other molecules or other parameters.
Right. And
so that's all good. So that's for all the gaseous part, and we are quite pleased to know that it's highlighting all the important region that we think that we as astronomers think that is important, and we can see the neural network is actually learning those instead of just simply memorizing. The other day I got a question from Collins say, well, what else can you learn if you put the data in the neural network? Must be able to learn all this molecular signature. But when it comes to learning, you can think of I think that you can think of neural network as a cheeky high school student who try to cheat his or her way out. You will find the best, the easiest way, the painless way to go through. So yes, you may think that is a natural way, but if you think about us when we try to learn a very difficult math problem, one way out is that you memorize the steps. That's it. You don't have to you don't have to know the concept. So yeah. So that's basically one very reassuring evidence that the neural network is actually relying on these molecular features. And for the other side, for the right panel, for the cloud and temperature and radius, you can see that the neural network is actually concentrating on the same region. Yeah. So they're actually sensitive for different quantities, but then they look quite similar, and is an evidence that the degeneracy between them the neural network is actually picking up the geometry between them. And that's why regions, they are actually highlighted, similar regions are highlighted, because it is relying on the same region to extract this information.
Right. 2 to 4. Yeah. Very cool.
Yeah, 2 to 4. And then you can also see that the photometric point on the far left.
Yes.
So especially on radius of the planet, is a pink, is a bright yellow, meaning that if you change that point, the neural network is like, no, that would be, I'm really sensitive to this point. And that's actually because that's the photometric band, and that basically probes the lower end of the atmosphere. That would give you the most accurate radius of the planet.
Yeah,
that way.
you can see this yellow dot both on the cloud top and in NH3.
Yeah.
Yellow,
so it's quite important in some cases as well.
Yeah, okay, that makes sense.
Yeah, so that basically brings us largely to the conclusion of the paper. So what I have missed out, actually, I've missed out quite a bit of stuff, which is the so I've actually trained 3 networks, as I mentioned early on, but then all these results, they're actually coming from one single one, which is the CNN one.
Okay.
We picked it because it has the least amount of parameters, so it's the simplest one. But we've also provided the sensitivity map and bias variance decomposition for the other network as well. And long story short, they also look quite similar to the CNN one, and that's why I've only gone through the CNN one. But then people interested, they can also look at the other ones as well. What we are trying to say here is that we introduce a number of tools that you can use to analyze the prediction from the neural network, especially in the case of exoplanetary retrieval. At the same time, we've also used the perturbation-based method, so sensitivity tests, what we call it, to peek inside the neural network to see which part of the regions is important for its prediction. And quite reassuringly, it's showing us that actually it relies on the molecular features.
Right.
Yeah.
Very cool.
So that basically wraps up the entire paper. So I'd say this paper is more of a methodology paper where we introduce the tools, and then it's up to the committee. Okay, now that you know the tools, you can use it in your own research. Yeah.
Very cool. I like this little epicycle comment here, right? Right for the wrong reasons. Epicycles.
Yeah.
Oh, very cool. Gordon, thank you so much for walking us through the peeking inside the black box paper. It's very nice.
Thank you very much. My pleasure.
Sure. And you kind of hinted at it a little bit toward the end there.
Yeah.
So where does the community go, let's say, over the next couple of years on this line of research? Do we continue to take a look at other machine learning algorithms? Are there additional data sets one could apply this to, or what are your plans to apply this to? So
in terms of interpretability, let's say, so explainable AI, which is basically a subdiscipline within the machine learning community, which aims to basically develop AI that is fully explainable. What we have done here is basically a tiny baby step. So we know that the input features, the molecular features are quite important, right? But what is this decision step from input spectrum to the output? What is the decision pathway?
Right.
How does an AI use this kind of information? Now we know that they are important, but how important are they, and in what way they're important? Okay. So I think, in my opinion, we're still a long way to go in terms of interpretability, but I think it is definitely a worthwhile research direction to go ahead. Yeah, because if you want, we are. I mean, I am at least naturally skeptical about this. Like, if we can't explain it, if we can't look into it, how can we know whether it's going on? You know, it gives me a nightmare at night. So I think we should definitely go ahead and sort of dissect these kind of new network models and look into it and see what is going on.
Yep.
Yeah, and then on the other hand, there are also emerging problems when we have JWST, when we have aerial coming online, is that we have these high quality spectrum right now. But then if you are using MCMC or nested sampling method on this kind of spectra, high resolution spectra, we will spend days or even weeks to basically decipher this information. Is there a better alternative? Because we will be looking at hundreds, or if in the future, thousands of these exoplanets, atmosphere of these exoplanets. Is there a more efficient way of doing that? And what we're seeing right now is that machine learning techniques could be a good alternative to basically doing population study of a large number of these exoplanets. That would be the dream, but yeah, that would be not in the next 5 years, but in the next decade. But then I'm hopeful of this.
Yeah. No, dreams are good. Having an ideal end state is good for pointing directions. So it's great. Very cool.
Thank you.
Well, Gordon, I want to thank you once again for walking us through your really lovely paper. Thank you.
Thank you very much for the opportunity. Yes.
And that will do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.
Bye-bye.